Welcome to my video lecture based on electric circuit theory, paper code PCEE 301. It is based on the syllabus of Markout curriculum. Today my topic is incidence matrix and triset matrix of graph theory. Myself Rumun Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra Sur Institute of Technology and Sports Complex. Previously it was known as Dr. Sudhir Chandra Sur Degree Engineering College under GIS Group. In this lecture we will highlight about the incidence matrix and triset matrix of graph theory. In my previous lecture we have understood what is the concept of graph theory and how the incidence matrix is basically formed, and what is the branches, what is node, how we can form tree, how we can form link or trees. Those things we have learned in my last lecture. In this lecture we will go on about incidence matrix and triset matrix and how it can help in graph theory, that we will see through different examples. So we will start with incidence matrix and KCL, Kirchhoff's current law. Let us, for this given graph, which is shown in the figure of 4.6, Kirchhoff's current law for the branches I1, I2, I3, I4, I5 and I6 gives the following equation. See what are the equations? Here, this is I1, I2 and I6. All these three branches are connected in the node 1. So our first equation is I1 plus I2 plus I6 equals to 0, because we know that in Kirchhoff's current law, summation of currents meeting at a node equals to 0. And here the direction all are leaving from the node. So we have taken the positive I1 plus I2 plus I3 in the node 1 equals to 0. Next we will go to the node 2 and we can see there three branches are connected, I1, I3 and I5. Among these, I3 is leaving, I1 and I2 are entering. That means I1 will be minus, I5 will be also minus and I3 will be plus. So the equations ultimately it will be minus I1 plus I3 minus I5 equals to 0. That is the second equations we have formed in node 2. In node 3, the equation will be, it is connected with branch 2, 3 and 4. Branch 2 is entering, branch 3 also entering and branch 4 leaving. That means branch 4 will be plus and branch 2 and branch 3 will be minus. So the equation will be minus I2 minus I3 plus I4 equals to 0. In a similar way, we can write the equation in the node 4, that is minus I4 plus I5 minus I6. In that way, we can form all the equations of node 1, 2, 3, 4. That is the KCL, application of KCL in form of graph theory. Now, using those equations, we will form the incidence matrix. Okay. So, incidence matrix will be combination of 1 and 0 based on which branch is connected with node or which one is not connected with the node. Here we have 6 branches. That means our parameter will be 1, 2, 3, 4, 5 and 6. That means 6 branches. And 6 branch means 6 currents. Definitely that is I1, I2, I3, I4, I5 and I6. Now with help of this equations we can form this incidence matrix, or we can directly form it from the graph. Let's see from the equation. Our first equation is I1 plus I2 plus I6. That means in place of 1 it will be plus 1, in place of 2 it will be plus 1, and in place of 6 it will be plus 1, and remaining all other branches are not connected, so it will be 0, 0, 0. Okay. Similar way, see, in place of I1 it is minus 1, so it is minus 1. In place of I3 it is plus 1, so it is plus 1. In place of I5 or branch 5 it is minus 1, so again it is minus 1. In that way, we can form the incidence matrix of KCL. That means our ultimate thing of incidence matrix is AAIB equals to 0, where AA is the complete incidence matrix of the graph and IB is the branch currents. Okay. So in that way, we can form the incidence matrix of Kirchhoff's current law. This is the application of graph theory in case of Kirchhoff's current law. Next one, reduced incidence matrix. In my last lecture, I have already highlighted what is reduced incidence matrix. Reduced incidence matrix means we will just delete a complete row. In general, the lower row is deleted. So, we have deleted the last row here. This one we will delete. This part we will delete, and definitely the matrix will be 1 minus 1 0, 1 minus 1 0, 1 0 minus 1 0, 1 minus 1 0 0 1 0 minus 1 0 1 0 0. See, this is that matrix of reduced incidence matrix. That means we are just deleting the last column of the reduced incidence matrix. Now, from the reduced incidence matrix, we can also get the incidence matrix also. And the way we are getting incidence matrix from reduced incidence matrix is we have to sum up all these values, and if this is 0, then it is correct. That means what will happen? Let's see, this is minus 1 plus 1, that means 0. Minus 1 plus 1, that is 0. 1 minus 1, 0. And here we need minus 1 to get 0. Here we need plus 1 to get 0. And here we need minus 1 to get 0. That means all this column value will be 0. So, by adding this 1, we can get the incidence matrix in that way. Now, incidence matrix and Kirchhoff voltage law. Kirchhoff voltage law means summation of voltage drops in a closed loop equals to 0. We are taking the same figure of 4.6, this one, same figure, and we are forming the Kirchhoff voltage law. So here all the voltages will be VB1, VB2, VB3 like that way, VB6. That means 6 branches, so we have 6 voltages. Can be represented in terms of node voltages like VN1, VN2, VN3 like that way. Okay. So node voltages, there are 4 nodes, so node voltage will be also number 4. So it will be VN1, VN2, VN3, VN4 like that way. So definitely our branch voltage VB1 will be in between node 1 and node 2. So this is VB1, this one VB1. So it will be VN1 minus VN2, that is equals to VB1. Similarly, node voltage 2 in between 1 and 3, so it will be VN1 minus VN3. So in that way, we can write all the branch voltages VB1, VB2, VB3, VB4 up to VB6. We can write in that way. Now, the Kirchhoff's voltage law matrix we will form. So, definitely the VB1 will be Vn1 minus Vn2. That means in place of 1, Vn1 it will be plus 1, in place of Vn2 it will be minus 1, and remaining 3 and 4 will be 0. That is this one. Okay. In case of Vb2, Vn1 and Vn3 are present. That means in place of 1 it will be plus 1, in place of 3 it will be minus 1, remaining 2 and 4 will be 0. So this is that one. In that way we will form the total incidence matrix of KVL equation, and it will be incidence matrix into the node voltages equals to the branch voltage. That means A transpose Vn equals to Vb. Basically, it is the transpose of incidence matrix into node voltage equals to branch voltage. In that way, we can represent the incidence matrix and Kirchhoff's voltage law. Now, the properties of complete incidence matrix. There are mainly 3 properties which we can highlight here. That is, the sum of entries in any column is equals to 0. Secondly, the determinant of the incidence matrix of a closed loop is 0. And thirdly, the rank of incidence matrix of a connected graph is equals to n minus 1. That means the number of node minus 1 equals to the rank of that incidence matrix. Okay. Next, the number of possible trees of a graph. This one, the number of possible trees of a graph. The number of possible trees of a graph equals to basically determinant A into A transpose. That is, indicates the number of possible trees of a graph. That means, if a graph is given and you have to determine the number of trees of the graph, for that case, you have to first form the incidence matrix, then A is the incidence matrix multiplied with A transpose, and the determinant of this whole A into A transpose equals to the number of possible trees of that particular graph. Okay. Where A is the reduced incidence matrix obtained by eliminating any one row of the complete incidence matrix, and A transpose is the transpose of the matrix A. Okay. So in that way we can determine the number of trees of the particular graph. So let us take an example. For the graph, same graph, 4.6 figure. The complete incidence matrix is this one, which we have already calculated. Now the reduced incidence matrix is this. That means we have eliminated one row. Thus the number of possible trees will be determinant of the reduced incidence matrix multiplied with the transpose of reduced incidence matrix, and their whole determinant will give you the result of the number of possible trees. So here we are getting that number of possible trees for the given graph, which is shown in the figure 4.6, that means this one, and this graph is basically have 16 number of trees. The number of possible trees for this graph we have calculated, that is 16, 1, 6, that we have calculated here. So now we will go to Tye-Set matrix and loop current. So what is Tye-Set matrix? Tye-Set is a set of branches contained in a loop such that each loop contains one link or cord and the remainder are tree branches. Okay. So what happens? Tye-Set is a set of branches contained in a loop such that Each loop contains one link or cord and remainder are tree branches, that is known as dissect. Consider a graph and the tree is shown here. Like this is the graph and we have removed all the branches which form the loop. That means a graph without any loop, that is basically a tree. So this is a tree of this graph. And now we will see that the loops are present in the graph. That is the loop. This is the first loop, this one, and this one is the second loop here, and this one is the third loop here, and that part is separately shown here like this: loop 1, loop 2 and loop 3. So fundamental loop 1 is basically connecting link 1 to the tree. Next fundamental loop, that is connected link 5 to the tree. Third fundamental loop, that is connecting link 6 to the tree. So these sets of branches 1, 2, 3, 2, 4, 5 and 3, 4, 6 form 3 dissects of this graph. Okay. So whatever loops, individual loops can be formed from a tree, that is basically the dissects. So here we have got 3 dissects that will combine this one, 1, 2, 3. This is one dissect. Next 2, 4, 5 another, and 3, 4, 6 this is another dissect. Okay. So dissect matrix or loop incidence matrix or circuit B matrix. It is represented by BA, capital B suffix A. Is basically representation of dissect matrix or loop incidence matrix or circuit matrix. For a given graph having n nodes and b branches, dissect matrix is a rectangular matrix with b columns and as many rows as there are loops. Its elements have the following values, that is Bij equals to 1 if the branch j is in loop I and their orientation coincides. That is, the loop current and branch current flow in the same direction. Loop current and branch current are flowing in the same direction. Second, Bij equals to -1 if branch j is in the loop I and their orientation do not coincide. Next, Bij equals to 0 if branch j is not in loop I. Okay. So, the example is for the graph shown in figure 4.8a. This is the graph 4.8. This is the graph. And tree selected in the 4.8b. Tree means we will remove all the loops and the remaining part will be basically the tree. This is. The loops are here. This one, and this one. These are the 3 loops. That means for removing this loop we have to omit maybe this branch. We can maybe omit this branch. Or we can omit this branch. So that will form the tree. So here the dotted lines they have omitted. So it will form the tree. So here the link is basically 4, 5 and 6. These are the links which will omit the loops. That means those are the links. So from there we can form the dissect matrix using these 1, 2, 3, 4, 5, 6 branches and whatever the relationship with the links 4, 5, 6 that we have highlighted here, and that will form the dissect matrix. See first 1, 2, 3, 4, 5, 6 link 4. Link 4, it means this one. What is the relationship it has? it is connected 1, 2 and 4. Okay. 1 it is entering, 4 it is leaving, and 2 it is in opposite direction. That means 1 and 4 will be plus and 2 will be minus. Next, in link 5, this one. See the loop. It is connected between 2, 5 and 3, and the direction of 2, 5 are same and 3 is in opposite. That means 2 and 5 will be plus and 3 will be minus. And in third loop, it is combined between 3, 6. Between these two, and both have the same direction. So both will be plus and remaining all will be 0. That is the triset matrix we have formed here. So in this lecture we have learned about incidence matrix, reduced incidence matrix, triset matrix, relationship between Kirchhoff's current law and incidence matrix, relationship between Kirchhoff's voltage law and incidence matrix. In that way, we can easily understand that the graph theory is very helpful for different circuit analysis problems like implementation of Kirchhoff's current law, voltage law is possible in case of graph theory, and it is very easy. And this module is very simple and easy to answer in for exams. So definitely this module is very important for semester exams also, and it will be very easy for students to answer the question related to the graph theory. So I will tell that all the students must practice different problems related to graph theory, and it will be very easy for you to give the answer in case of graph theory. So not much more today. Thank you all for listening my lecture.